All right. Good morning, afternoon, evening, whenever you're watching this. Happy spring. I hope you had a wonderful spring break. And today we're sort of going to just jump right into this. Okay. So, just as a reminder, this is a 2-day PowerPoint worksheet combo. So if you start this on Tuesday and you're not finished, you're going to finish this on Wednesday, whether you're in person or you're in school. So make sure that you're working on this PowerPoint video and worksheet sort of combo. So it's written to give you guidance. I'm also making this video just to make sure that you have some additional guidance. But remember, anything that you didn't finish in class or you didn't finish on Tuesday needs to be finished at home. If you're at home today on Tuesday, make sure that you are starting this so you're not behind on Wednesday. There's also a little coloring sheet that if you come to school, you'll get. It's about, actually, I'm not one acting silly. It looks like this. It's going to be a half sheet, okay, front and back, with a short little coloring exercise to get you more familiar with the homologous structures, which we will talk about in a little bit. So, sort of just a basic schedule, gonna do a quick introduction, talk about theories, fossil records, comparative anatomy, molecular biology, and then just want to wrap it all up together. There will be points in the video where I pause to give you a chance to pause. Well, hopefully you'll actually pause. You'll pause the video and you will do the worksheet questions and just kind of get that rolling. Okay. So it's spring, birds are chirping, the flowers are, I don't think I've seen any flowers blooming yet, but they're getting there. Flowers are blooming, grass is getting greener. We see trees getting their leaves back. We see every year, approximately every 3 months, these small changes that seem so big to us as people. But we really want to think about change on a bigger scale. We talk about years, decades, millennia, eons. We can start thinking about how plants, animals, and other organisms have changed over time. So, when we talk about this idea of change over time, that really just means we're talking about the theory of evolution. So, I'm sure you've heard the word theory thrown around a lot. Now, I've got three different definitions here, in addition to my own sort of paraphrasing. But a theory is this: it is a set of principles or sort of not observations, sort of principles or statements that gives us a step by step understanding of something that we see in the world around us, a natural phenomena. We test them, we independently verify them. So scientists over here, scientists over there, scientists back there, and front here, they all do their own testings and they start to come to the consensus or the agreement that, hey, this makes sense. So this is not, when I think a lot of people, when they hear the word theory, they can often think of unsubstantiated or false. But what we're really looking at here is something that has been tested. I mean, at this point, it's been decades since we started really digging into it. But something that's been tested vigorously by science and has been accepted by most of the scientific community. And not only that has it been tested, but we can also predict future occurrences. We can predict how something will happen based on those statements or principles that we came up with. So, you have, hopefully, if you haven't already, I'll put the link in the description just in case you might need it, but you need to make a copy of the FAM or FAM Evidence of Evolution worksheet. Okay, if you're working on Canvas, you've already clicked this link or you've already grabbed the worksheet, but you should have this open in front of you. Okay, so you'd click that. Let me just show you what it looks like. It says you want to make a copy, you're going to say absolutely. You're going to wait for it to load. Fantastic. So something, we're gonna just, if you click too fast, it starts getting cranky. So where it says copy of, you're gonna edit that title and you're gonna put in your name. All right. All right. So let's go back to the PowerPoint. So big parts of the evidence of evolution. Three big parts that are substantiated, supported by fact. F is for fossil record. A is for comparative anatomy. That's where the A comes from, anatomy. And then the M is for molecular biology. All these two-word names here. All right. So let's take a look at fossil records first. So quick reminder, what is a fossil? I personally was not into dinosaurs very much when I was a kid. My brother was, I just wasn't. But here's the definition of a fossil. It's a remnant or leftover, impression, trace, or a trace of a organism that is long dead. Okay, so it's either preserved in rock or amber or other substances. We can see all sorts of types of fossils here. So questions 1 through 3 on your worksheet, I want you to pause this video. I'm pausing the timer because it started playing music and I couldn't focus, but pause this video for about 5 minutes. Work on questions 1, 2, and 3 on your worksheet. All right, so that's questions 1, 2, and 3 right here on your worksheet. Go ahead and pause the video, work on those. All right, so want to sort of discuss. I know if you're probably at home and you're just watching the video, obviously I can't really discuss with you, but think about this. What did you really see? What are these comparisons between these horses? Here are some of the ones that I noticed. I noticed that if I look at their skulls, right, this is the modern horse. This is the one that's closest to where we are living. This is like, I don't know, what are some horse names? Um, Coulter or something down the road. You know, you see a horse on the side of the road. That's this type of horse, the equus or the modern horse, all right here on the left side. The oldest horse is the Eohippus, and everything sort of in between the Mesohippus, the Merychippus, Pilohippus, all the way back up to Equus. And so when I notice, okay, this is the oldest, the Eohippus has such a small head, and it's got almost fingers for feet. Looks like it's got kind of standing on those little fingers. And so I see, okay, the heads got bigger over time, right? So I noticed that. I see that. Looks like, okay, we used to have like a bunch of fingers. And then as I moved, not only did they get longer, so you see how they actually got longer, like one of those fingers just kept getting longer, but they stopped having so many fingers. It's like their fingers, just one of them just got more important. And so you had, I'm having a hard time kind of showing it, but you kind of ended up with a hoof. And so this is the weirdest thing about horses. They're literally standing on what we would call our index fingers, just the horse tapping around. So those are some of the things that I notice. Okay, I noticed they're increasing of size in general, both the skulls and the legs. I'm looking at the increase of size of the hoof, because we didn't start with a hoof. We started with a very, very small fingertip, right? And then we ended up with a hoof. So those are some of the things that I noticed. Now, fossil records alone are not enough evidence to show us that evolution is a thing that happens. We have to use these 3 pieces of evidence and more. This is just the basics. The 3 pieces of evidence to give a overall understanding of how evolution happens, how we can prove that it works. So, just remember the rocks on the bottom are the oldest rocks, and it just sort of stacks up. So the further you go down into the crust, the older the earth is. So for example, the Eohippus would be all the way down, and the Equus, if there are any, because well, there are. If the Equus fossils would be all the way at the top. Sorry, I can't see my hands. So oldest, youngest fossils. Okay. All right, so A is for comparative anatomy. Talking about anatomical comparisons. What in the world? What is anatomy? Okay. And so anatomy is the science of the shape and structure of organisms, not how they work, but just the shape. How, oh, there's a hole in my jacket. How your arms are structured, how your fingers are structured, how your ears or your earlobes, your muscles, your nerves, how everything is structured and shaped. It's not just humans. We can have anatomy for plants. We can have, I mean, even anatomy for, fungi, bacteria, but any organism. It's just the structure and shape of their parts. Okay. So looking at anatomy, you're gonna take about 8 minutes. Don't overthink it. Don't panic. Don't be like, I'm gonna get it wrong. Take 8 minutes. Listen to this lovely timer if you can. All right, I'm gonna share the other tab. Excuse me. Take those 8 minutes. I want you to answer questions 4, 5, 6, 7, 8, 9, 10, and 11. I know it's like, wow, it's a lot of questions. Don't worry. It's not gonna take as long as you think. So 8 minutes, pause the video here and work on those. All right, so hopefully you did work on those because I know you paused the video. I know you took those 8 minutes or however long it took you. It might have taken you 5. Awesome. So sort of working on what are you noticing about these different types of structures. And so we're going to talk about what these structures are. You had 3 little sets of questions, 3 examples. We're going to talk about what each of them means. So down a little bit lower, you have the summary with these blanks in orange and green. And you're going to put in what you see on the slides here. So first type of structures, we have 3 main structures, are homologous. Kind of say that in your mouth, but kind of feels like a weird jelly bean. Homologous. Okay. Homologous structures. Remember, think about, I know, think all the way back, okay, to homozygous. And what do we always say the homo meant? Same. So homologous structures, meaning the same type of structures or the same the same logic of the structure, the same purpose. All right. But it's a little bit different. So sorry, the same structure. So homologous structures show individual variations on a common anatomical theme. And so that could be, most often we like to talk about our forelimbs. So a forelimb is the limb that is the closest to the head. Okay. And so I've got a forelimb, but if you look at the bones of my forelimb, you can see similarities to bones of the forelimbs of many other animals, such as cats, birds, bats, lizards, crocodiles, horses. You can go down the list. And so when we see these common anatomical themes, okay, I've got the humerus, I've got the radius, the ulna, the metacarpals, no, carpals, metacarpals, phalanges, like you see all these common structures, you can usually tell there's a common ancestor there. At some point in very, very long time ago, we shared ancestors with all of those animals. So in particular, in this activity, what we were looking at for that one was the human and the cat limb. Okay, so homologous structures, different function, same structure. Okay. Now, this is a meme you might have seen on the internet. I know I saw it on the internet and I immediately said I have to put that in the slide. Okay, but tetrapods is the same. They're not the same, but they're descended from the same common ancestor. So now you kind of understand this a little bit more. I might have taken the fun out of it a little bit, but you kind of get it a little bit better now. Because in this looks like we got a turtle, a human, a horse, a bat, no, that's a bird, a bat, and a seal. My goodness, my eyesight is incredible. All right, and so we actually can see how all of these, see how these are colored in? So this is all blue, those are all the humerus. Even though they're different shapes, they still have that same anatomically homologous structure, same order, same connections, same bone structures, but they've been modified over time through natural selection in order to give them their best advantage for that particular creature. All right, next is analogous structures. So filling in the blanks again. So analogous, all right, and then now it gets confusing. So analogous have different anatomy, same function. Okay, so let's take a look at our worksheet. Which of those would that have been? And we're going to look in, same function, different anatomy, the butterfly wing and the bird wing. So they both function to fly. That's what they do. That's what they're used for. However, they have a different structure. Birds have bones. Butterflies don't have bones. All right. Birds have feathers. Butterflies have scales. There's a lot of differences between them, but they do the same thing. However, just because they both fly does not mean they are related. So that is not evidence of evolution. Now, it doesn't mean they're not related. It just means we can't use it to say they're related because it is not actually based in the type of evidence that we need to prove evolution. So our example again, butterfly wings, bird wings. Same function, different structure. Again, same function, different structure. We got, sorry if you're not a fan of staring, I should have put a warning on that, but octopus eyes, we got human eyes, we got spider eyes, insect eyes. Their function is to provide vision, to see, but they all have very different structures. So again, trying to compare those analogous structures, yeah, they're streamlined, they're zooming through the ocean. Okay, they've got these flippers. But homologous structures are, sorry, let me just focus on that. So analogous is same function, different structure. Homologous is same structure, different function. Human hands are made for hugging and grabbing. All right. Cat hands, she's asleep. I don't want to bother her. But cat hands are made for, clawing and walking. Whale hands or forelimbs are made for swimming. And of course, bat forelimbs are made for flying. All right. So vestigial structures are actually just kind of fun, but they are very important for determining relatedness or determining whether something has a common ancestor. So these are remnants. If you've ever heard of someone who had to take their or had to get their appendix taken out, the appendix is usually a good example of a vestigial structure. It no longer serves the purpose that it used to serve when we were like older humans. So like what type of common ancestor might have needed the appendix, but eventually we no longer needed it. Natural selection didn't select against it, so it just kind of hung around. I really hope my internet doesn't go out. Okay, let me just hurry and keep going. So the last thunder's got me all frazzled. The last oh no. The last example was the cave fish, right? So we have this really cool picture, and like these are just wild to think about. We've got these fish here. Two of them are minnows, and they have eyes. But that's not a dead fish. It's not a broken fish. It's not deformed. That is a cave minnow or a cave fish that after a long period of time, after living in the darkness, it was more beneficial not to have eyes. So natural selection selected against eyes, and now they don't have eyes. So you could say their eye socket, which is where your eye sits, is orbital socket, they still have that. They don't need it because they don't have eyes. So that would be considered a vestigial structure. Or if they had any sort of eyes left over, that would be considered vestigial because they're not using it anymore. Okay. So that is evidence of evolution because we can see, okay, it started to sort of phase this out through natural selection through the process of evolution. But it actually tells us that those minnows and the cavefish do have a common ancestor, that they are closely related. Pretty neat. So, just to give you some food for thought, some other vestigial structures in humans, goosebumps. You get goosebumps. You ever see a cat get big and scary when it gets scared? We don't need to do that anymore. So we don't really need that function of our goosebumps. It does serve some other functions, but for the most part, if that were the function, it wouldn't be helpful. We don't need our ear muscles. We don't have ears that move around for listening or for, expression. And we have a tailbone. That little, if you ever heard you say you hurt your tailbone, right there at the beginning of your butt, there's a bone that if we had tails, we would need it because we have a tail, but we don't have tails anymore. So that bone's just kind of hanging out. We don't really need it anymore. Some other examples of vestigial structures in animals are wings and birds that don't fly, like ostriches, emus, useless hip and leg bones in whales and snakes. You can actually see on their skeleton, there's like a teeny, 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 teeny couple of bones there that used to be hips and legs. And then those leftover toe bones in the horse. If you zoom in on these slides at a later date, you can actually see. But remember how those horse bones just came to be that one finger? They don't need the rest of them, but they're still kind of hanging out a little bit. There's just a few floating sort of bones. So those are leftovers. So, big conclusion, homologous structures, vestigial structures are part of evidence for common ancestors and relatedness, evolution as a whole. Analogous structures are not evidence of evolution. All right, so big conclusion slide, very good slide to jot down in your notebook or maybe take a picture of, try to memorize. Last but not least, for what we need to know, M is for molecular biology or biomolecular comparison. So this is one of my favorite things to do. Let's look. It's kind of like those highlight things where you spot the difference. So you'll see on your worksheet that there's a bit about cytochrome C, but let's just focus on finding the differences here. We can explain that in a second. If I find my pointer, there we go. So let's look at these. So we have a whale here and a cow here. We're going to compare these segments because what we know is that all mammals have this particular amino acid sequence, but the fewer differences, the more related they are. So let's see how closely related a whale and a cow are. So we can sort of follow in the middle. That's what I like to do. I just kind of put my pointer in the middle and I look for any differences. There's no differences here. Okay, gonna go, 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 go. Nope, no differences here. Go, 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 go. No. Oh, there's one. Okay, so we got A and E at the end of the third section. Oops. All right, A and E there. So that's one difference. All right, go, 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 go. Wow. Okay, so there's one single difference between whales and cows. Pretty cool. Let's look at whales and chickens. All right, go, 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 go. Nope, nothing in the first one. Go, 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 go. Nothing in the second one either. Go, 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 go. Ooh, one. Go, go, two. Okay, so we got two differences. Go, 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 go. Ooh. Three differences. Incredible. So we had one difference between whales and cows and one difference between whales and cows and three differences between whales and chickens. So less differences, more related. So a whale is more related to a cow than a chicken because they have more in common. Again, this is not enough alone. But when we talk about biomolecular differences, we can be talking about DNA, we can be talking about amino acid sequences, all sorts of other sort of biomolecular stuff. Things that are too small to see, talking about the way that our bodies put together chemicals, those are all ways to compare the relatedness of species. So take the next 8 minutes, pause here, do page 3 of the worksheet, the chart and the question. All right, if you're working in class and you've been working, make sure this is around the time where I'd expect you might start running out of time if you're sitting in school. Make sure you finish this while you're at home tomorrow, all right, and get that turned in. So yes, pause here for about 8 minutes to get this done. All right, so just sort of in conclusion here, molecular biology about amino acids such as the cytochrome C, DNA, protein sequences, other indicators on molecular levels that is encompassing what we talk about molecular biology. And so the main idea is this: fewer differences, more related. More differences, less related. Okay? So we're just kind of comparing animals to animals. Oh, I'm so sorry. Forgot to say. We kept going here. Oh no, there it is. So this is where you're not comparing it to whales, but comparing it to humans. So this is your human one. You want to keep that in mind, and then you just go through, compare. You want to go through and compare each of these animals, and then you're going to highlight where you see differences. All right, and so remember to highlight, you're just going to highlight it with your mouse, and then you're going to you can change the highlight color up here at the top. Or you can change the text color, or you can bold it, anything you want, as long as you can tell and your teacher can tell what you're saying is different from the human strand. All right, have fun with that. It's very colorful. Just list those down there and then complete questions 12, 13, and 14. And then you'll be done with the worksheet. All right. So, one last thing to kind of bring it all together. I know I've talked, oh my gosh, probably way too long. But this video is one of my favorite videos ever. One, because whales are cool. Two, because it's a really good overarching way of stating clearly how all the evidence for evolution comes together when we look at one particular species. It really helps us sort of focus on that and kind of see how it works together. So when you get a chance, please watch that video. I hope this video was helpful to give you the foundation you needed to get. Sorry, I just realized I was on the wrong slides. Hope this video was helpful to give you the foundation you need to work on that worksheet. If you need any questions answered, send emails to miss.why.bio@gmail.com. I'll be more than happy to answer them. And stay curious.